Okay, guys. So yeah, I'm back. Sorry about that. I have to find a charger for my laptop. So yeah, where were we? So basically, this is the flow sheet that I will use to simulate biomass pyrolysis processes. Let's see. I have tried. As I said, I'm not gonna waste my time on arranging all of this, but this is pretty much how it's gonna look. Okay, after that, I need to specify my feed stream. Just double click or hit next if you want. Um, okay, here's the thing. You have a mixed substream. You also have a CI solid substream. You also have a non-conventional solid substrate. I'm going to use a non-conventional solid substream because my my feed is basically biomass, wet biomass, and it is a non-conventional component. So I have to use a non-conventional solid substrate. So just type temperature, 30 degrees Celsius, 1 bar. The flow rate here is 50 kilogram of wet biomass. Now it's done. Technically it's not done. As you can see, you have this thing. You expand it. As you can see, you need to provide approximate analysis of a wet biomass because the material going into a dryer is a wet biomass. So you have to provide a approximate analysis of wet biomass. So here, moisture is 7.86, fixed carbon is 13.94, volatile matter is 84.71, ash is 1.35. So when you add all of this, become 107.86. So you add ash, volatile matter plus fixed carbon will become 100. Now you go click here, you will need to specify ultimate analysis. All right, ash should be 1.35, should be the same. So just type 1.35. Carbon is 47.67. Hydrogen is 6.86. Nitrogen is 0.13. Chlorine is 0. Sulfur is 0.01. Oxygen is 43.98. Now you have specified your ultimate analysis. The final one is your sulfur analysis. Now your sulfur analysis, the total should be 0.01 because it should be equal to sulfur component in your ultimate analysis. So here 0.0033, I'm sorry, because the author of the paper assumed that it is equally distributed. So just divide by 3. So basically you have specified all of it. The last one that you need to specify is particle size distribution. Just double click here. Now your particle size distribution should be millimeter. These are micron if I'm mistaken. So edit. Number of interval, if you see the particle size distribution, I only have 4, I think. Let me check. You have 5 interval. So I change interval from 10 into 5. Okay. And then size unit should be millimeter. Choose. Now lower limit is 1 to 4. And then 4 to 8. 8 to 12. 12 to 16. 16 to 20 millimeters. Okay, now that you have defined the interval, hit close. Now you need to provide a weight fraction. So 0 to 4 millimeters, you have 0.1. The next one is 0.2. The third one is 0.35. The fourth one is 0.2. The fifth one is 0.05. Okay, there's a 0.1, 0.2, 0. Okay, I made a mistake, should be 0.1. 0.15. Okay. So there's a correction in the data. So the total should be 1. So in here, I just change it to 0.15. Correction. So 0.05 in the slides, change it to 0.15. Okay, now that you have defined particle size distribution, you have defined your component attributes, then you can close, and then you can define your inert. So your inert is basically, let's see, it is an inert gas at 30 and 1 bar. Flow rate is 0.5 by mass, 0.5 kilogram per minute, 0.5 kilogram per minute. Mole composition is, mole fraction is 0.99, 99% of nitrogen. The rest is oxygen. Where's my oxygen? Did I not? Okay, here's my oxygen, 0.01. Okay, now that you are done, I will specify the easiest one first. I will specify this air cool here. Temperature is 300 degrees Celsius, pressure 1 bar. I will specify water cool 40 degrees Celsius, 1 bar. And then here is, I'm going to specify no pressure 1 bar, and then change to duty 0. Or you can also specify 40 degrees Celsius, it's the same thing. Okay, next, I'm going to start my drying process. So double click. Okay, my drying process occurs at 150 degrees Celsius and 1 bar. All right, here's my reaction. So the reaction, if you see the slide, is basically wet biomass, coefficient of 1, is converted into a dry, biomass and water, basically your moisture. Here is 0.9214. Okay, for water, I'm gonna assume 1. I'm gonna assume 1 first. How much is converted is 100%. 100% of wet biomass turned into dry biomass. Wet biomass. Now, how do I get 0.9214? It's quite easy. When you want to give a non-conventional to another non-conventional, 1 gram of non-conventional component is equal to 1 mole of non-conventional component, and same goes with the dry biomass. 1 mole of non-conventional dry biomass is equal to 1 gram or 1 gram of non-conventional dry biomass. So, okay, how do I get this? If you remember my moisture, if you see my approximate analysis, my moisture is 7.86, right? So, 100% of wet biomass consists of dry biomass, and 7.86% of okay, let me explain one more time. So when you have 100%, your wet biomass consists of 7.86% of moisture, and the rest is dry biomass. So 0.9214 is basically 100% minus moisture 7.86. You will get 92.14. So you divide by 100, you will get 0.9214. Now, for water, I'm just gonna assume 1 first. Later you will see why you will get error. I will show how to make the correction. So you do 1. Hit next. Okay, now in the dryer unit, right? You have a non-conventional component, which is your wet biomass, and then going out is a dry biomass, right? So for dry biomass, you need to specify what are their ultimate analysis, proximate analysis, and sulfur analysis for dry biomass. So for dry biomass, go to component attributes. Substream is non-conventional. Choose dry biomass. Wet biomass, no need because you have specified those earlier. So attribute, choose approximate analysis. Now for dry biomass, there are no more moisture. You can write down 0. The component is still 13.94 fixed carbon, 84.71 volatile matter, and a 1.35 ash. And then you repeat the same thing for ultimate analysis. Ash is 1.35. And then carbon 47.67. Hydrogen 6.86. Nitrogen 0.13. Chlorine is 0. Sulfur is 0.01. Oxygen is 43.98. Ultimate analysis done. Sulfur analysis is basically the same, 0.003433, 0.0033, 0.0034. The only difference here is dry biomass is exactly like wet biomass without moisture. That's the only difference. Next. Okay, next, we're gonna, okay, sorry about that. Next, I'm gonna use I'm gonna use R yield to simulate the decomposition of the dry biomass into its element, I'll say element form, you know, like hydrogen, nitrogen, sulfur, blah blah. So how can I do that? Just double click, set the temperature of, let's see, 500. So decomposition occurs at 500 according to the paper. But for drying, the funny thing here is for drying in the paper, they specify 500 as well. But in my case, I specify 150 because it makes more sense to for drying process to occur at 150 as opposed to 500. You know, because those are the first step of the pyrolysis process. Of course, pressure is 1 bar. Now yield, if you click yield here, component yield. So basically, component yield here, how should I, in the paper, they use a Fortran to do mass balance calculation of this, but I'm not going to do that. I'm going to use a simpler one where I'm going to do a breakdown based on their ultimate analysis, as simple as that. Now, if you remember, if you go to your flow sheet, right? My feed is basically a wet biomass. Coming out is a dry biomass plus moisture, water. In this case, I'm going to do a breakdown of biomass only. So I'm going to assume water being inert. Okay, because I'm going to assume breakdown of biomass only. So I choose water as an inert species. Now component yield. So my biomass, my dry biomass, will be decomposed into ash, will be decomposed into char, carbon, but it is a solid carbon, will be decomposed into hydrogen. If you check your elemental analysis, it is hydrogen monoatomic, you know, element, right? But, you know, after the reaction, it's not going to occur in the form of monoatomic hydrogen element. It's going to occur in a diatomic hydrogen. So, you know, that's how it works. And then same goes with element of nitrogen become nitrogen gas, and then element of sulfur become just sulfur, you know. Element of what else? Oxygen will become, you know, oxygen. What else? Am I missing something? Carbon, hydrogen, char, hydrogen, nitrogen, chlorine. I don't have any chlorine. I have sulfur, oxygen, and then ash. That's more enough. Now, Now, what are the bases? I'm gonna do a breakdown based on mass basis. Okay, let's see. Now, how many percent of one way to look at this is out of 1 kilogram of uh, dry biomass, how many percent is is basically ash. So if you remember your ultimate analysis, 1.35% is ash. So here is going to be 0.0135. So divided by 100, total should be 1, not 100. A char is basically a carbon 0.4767. It's basically, I'm going to do a breakdown based on their ultimate analysis, the simplest one. If you know your Fortran code, if you want to use a user supplied Fortran code, by all means, do that. I don't want to do that. Hydrogen is 0.0686. And then nitrogen, 0.0013. Check 1, 2. Yep, correct. Sulfur is 0.0001, I think. 1, 2. Yes. Okay. Oxygen 0.4398. Let's double check. Oxygen is 0.4398. Sulfur is 0.001. 0.0001. Nitrogen is 0.013. Hydrogen is 0.686. 4767. Okay, these are all correct. Okay, now that you have specified this, now in the R yield block to simulate breakdown of the dry biomass, you will produce another non-conventional component, which is ash. Now you have to specify ash component attributes. So just click component attributes, go to substream class, non-conventional, because you're going to produce ash being a non-conventional component. And an ID should be ash. You don't have to specify wet and dry biomass because this already been defined before. Attributes is proximate analysis. Now, these are quite simple. Ash is basically 100% ash, as simple as that. So the rest is 0, 0, 0, 100%. 100% ash. Ash is just ash. Ultimate analysis, same. Ash, 100 should be 100 as well. You can write down 0 for all, doesn't really matter. And then for sulfur, it's also 0. 0, 0, 0. That's it. Okay, after that, it goes to equilibrium Gibbs reactor. So all of the carbon, char, hydrogen, oxygen, nitrogen, inert gas will go into equilibrium reactors, and then they're gonna do equilibrium calculation where they're gonna keep whatever algorithm that they have inside. They will find out what is the best, what is the composition that give them the minimum Gibbs free energy. All right. So pressure here 1 bar. Temperature here is 500 degrees Celsius. So they're gonna do equilibrium calculation based on this pressure and temperature. Okay, now that I'm done, so the product after equilibrium calculation will consist of gases, various gases, plus char, which basically carbon, and ash. So gas phase will be removed, will go to the next stage, next steps. Whatever solid, including ash and char, will be collected below. So how can I simulate those? I'm going to use this substream separator. So double click. Now, I'm not going to define this. I'm going to define solid residue. Okay, at the bottom, I'm going to assume there are no gas whatsoever going into this stream. So 0. The rest, CISPD, is basically your carbon, char, if you will. Is 100% goes down. Ash, non-conventional, also 1. Okay, now that I'm done, I'm ready to run my simulation, but okay, you have to remember, but there will be an error here, drying. I will tell you why. But first, let's run the simulation. I hope it doesn't crash, but let's save it first. Save as backup file. Let's see. Yeah, I'm gonna save it here just to be on the safe side. No. Okay, now I can run. Let's have a look. It will give you error on the drying side, and then I will tell you how to fix it. As you can see, you have error on the this reaction. Now, because this reaction, this block is fine, it will be because it received a wrong information, then you would have uh, uh, some kind of like warning here. But let's check what is the error. So double click. If you go to say, is it comment or status? Let's see. Where's my status? Okay, maybe here. Now, under drying unit, you will see that block drying is not in mass balance. So 50 kilogram going in of feed must be 50 kilogram of dry biomass plus moisture going out. So that's how it is. So if you see, okay, if you see my feed stream, double click, go to result. And then I choose another one to do side by side. It should be a dry feed. Now, if you go down, now 50 kilogram of wet biomass, okay, turns into 46.07 kilogram of dry biomass. These are correct, by the way. You can check because uh, uh, like out of 50 kilogram, 92.14, I think, let me check, 92.14% of the mass belongs to a dry biomass. The rest are water or moisture. But as you can see here, water is 900. Obviously, these are completely wrong because mass balance is not conserved. So how can I, this is the result when I specify my reaction coefficient of water of 1. Okay, I need to change this so that the mass balance become correct. So how can I do this? It's quite simple. Go back to my material. Okay, I copy this one. I go to Excel. Where's my Excel? So I paste. Now, this one is coefficient. So if I choose coefficient of 1, water is 9 H2O, sorry, H2O. So this one's cool. So if I choose coefficient of 1, water is 900. I need to know what is the coefficient that give me 50 minus, if you remember, what is the flow rate? 46.01, because 46.01, 50 minus 46.07 is basically a balance. Balance should be water, right? So 46.07, 46.07. So technically you should get this number. Okay, but the question here is, what are the coefficient, the correct coefficient that will give me 3.93? Because if I choose 1, I will get 900. So it's quite simple. X should be, let's say I put here X. X should be this, no, it should be the other way around. This divided by this. Yes. Okay, you know what? Let me make it. No, let me make it like this. It's quite simple to follow. Now, what is the coefficient that give me this? So it should be this divided by this multiplied by 1. So this divided by this multiplied by 1. Now I should get this. I will copy all of it, copy, because if I choose like a few significant figures, it is probably not accurate enough to be within the tolerance. So I will copy all of the numbers. So I go back to my simulator, go back to my reactor unit, double click the reaction. Okay, paste the value. Okay, this is my coefficient, the actual coefficient that will give me a correct mass balance. So right click, hit next, hit OK. I should get a result. Oops. Okay, I still have a warning, but let's see what's the warning. But at least if you see my water going in, right? If I see my material stream, feed stream 50, dry feed should be 50 as well. Now mass balance are correct. The only thing that I need to take care of next is just a warning on the decomposition mass balance. So I have to check what is the warning. Okay, now they say missing reference of set outlet particle size distribution because I forgot to add particle size distribution of a dry biomass. So you go back to your, let's see, decomposition, go to component attributes. Let's see, how can I do this? Okay, go to particle size distribution. Okay, user specified particle size distribution of, let's see, so for substream of, okay, this one, okay, this is the particle size distribution of CISPD is my chart. Okay, if you refer my slides, there's a particle size distribution of char as well. So it should be, okay, I don't have it, but I'm going to assume char having the same particle size distribution. Also, I'm going to write down 0.1, 0.2, 0.35, 0.2, 0.15. Okay, I think this should be correct. These are, I'm sorry, these are for overall. Okay, again, mistake. These are for all of the non-conventional, including char as well. So hit next, should be able to get it done. Now I get a result. Okay. So overall over there is basically a particle size distribution for ash. No, sorry, for not for ash. Yeah, for ash. For what else? For char as well. I don't have char particle size distribution, but I'm just gonna assume they have the same particle size distribution. Okay. I don't want to go into details. But that's basically how you eliminate the warning. Actually, warning is not really that important in this case, so whatever. Okay, next, what are the requirement for our simulation? We need to calculate the solid residue, basically your char plus ash. Basically, that's your char, no, carbon plus ash composition changes with respect to pyrolysis temperature, and the gas composition here, how it changes as a function of temperature. Again, one way for you to do this is just keep changing the temperature, record the number, record the number, record the number. But I don't want to do that. What I'm going to do is I'm going to go to model analysis tool, go to sensitivity. Basically, we're going to vary a parameter and observe what are the effect of those parameters to whatever variables that you want to measure. So ID S1, just double click. All right, what are the parameters that we're going to vary? We're going to vary, click new. The parameter that will vary is, we will vary equilibrium I'll give temperature, because those are the things that do the final calculation. So choose, it is a block parameter, by the way. So just choose block. It is a block, so choose a block variable. What are the block? It should be equal. Okay, variable that we're going to change is we're going to vary temperature. So temp here. Unit should be degree Celsius. Okay, starting point is 350 to 750, if I'm not mistaken. Increment of 50. Okay, so they're going to collect several data based on 90 interval between 350 to 750. Yes. Okay. Next, you define what are your manipulated variable that you want to see the effects of it. So I'm gonna write a lot actually. So I have variables. Let's see. It's gonna be a hydrogen gas. It is a stream. Okay. And then the type is should be let's see, should I go mole flow or mass flow? I'm going to use mole flow. Should I use mole flow or mass flow? I don't really know because the paper, I think they don't really mention what is it. I'm going to use mole flow. But actually in the paper, yes, they say mole flow, so we're going to use a mole flow of gas stream. Substream is mixed because hydrogen is a conventional component for hydrogen. Okay, next is basically I don't want to repeat, so I'm just going to copy, and then paste. This one will become maybe nitrogen. No, maybe CO first. So CO, you click here, you change gas to carbon dioxide. Again, copy. You can do one by one, but I'm too lazy to do this. So CO2. Change the gas to CO2. Copy. Paste. Methane, CH4. Let's see, copy. And then copy. Paste. H2O, water. H2O. It should be water. Okay. Maybe I will rename as water. It's easier. And then I also need to add another variable, which is ash, because you need to find out what's the flow rate, what is the mass flow rate of the solid residue. So ash is basically a stream variable. It's going to be a mass flow of stream solid residue. Substream should be non-conventional, and then ash. Another one, I will add a char. A char is a stream, write down a mass flow. A stream should be solid residue. Substream is CISPD, conventional component but solid. So component is my char. Okay. Okay, and then I'm going to tabulate all of it. So I will tabulate column number 1, column number 2, 3, 4, 5, 6. Okay, I don't know how much. 7. So I will, how much? Water, methane, CO2. Oops. CO. What else? Hydrogen ash char. Okay, hydrogen ash char. Okay, now that you are done, just hit next, hit OK. Now everything is done. Go to result of sensitivity analysis. What I'm gonna do is I'm gonna copy this guy and then all of it. Right click, copy. I'm gonna paste in the Excel. I'm gonna paste values. So these are all of it. So as you can see, these are char and ash. What I will do is put maybe here, I guess. And then temperature, I'm just gonna copy. So here I will write down total. Should be this one plus this one. So here it should be a char weight percent. Okay. So should be this one divided by this one multiplied by 100. Okay, do the same. And then for this one, I will write down total. Sum of all this. And then composition, how can I do this? So it's basically this guy divided by this guy, dollar sign, multiply by 100. I think it should be like this. I could be wrong though. And then you do all for all gases. And then you do for this one as well. Okay, now I need to do a correction. This should be this guy. So this is basically a mole fraction, mole percent of water. More percent of water, more percent of this, of, let's see, escape of hydrogen, more percent of CO, CO2, more percent of CH4. Okay, should be 100. Okay, now you just need to do plot this guy and all of this. Insert maybe, yeah, maybe this. Okay, there's one. You plot this guy and then this guy. Insert, maybe choose this one. All right, so basically I have prepared two plots, but I'm not gonna do anything here. I'm gonna present all of my findings in my slides. So yeah, let's go to our slides. All right, guys, I have compiled the result. So the one on the left is basically result by this Visconti et al. From the paper. He got something like this. This is mine, where I vary pyrolysis temperature from 350 to 750 following his, and these are mole fraction without nitrogen. So as you can see, they are all the same, going up. For hydrogen, for example, it goes up and then stop here. For carbon monoxide, it is favored at higher temperatures. The red one, the purple one going down, the green one going down, the yellow one is also going down, and then these are all the same. So My simulation result is exactly the same gas composition in terms of like mole percentage with the paper. So it's good. My simulation is good. The next one is basically how char carbon percentage, okay, which will dictate your fuel energy, your fuel, your high heating value or low heating values, because more carbon in the char means it has a high heating values, but whatever. But as you can see here, as a function, if the pyrolysis temperature goes up, the char carbon start to drop down. But as you can see, they drops, mine also drops, and then these are around 95.7. They also begin 95.7, and then it drops to 91 point something. Mine also does. It is exactly the same. What does it tell me? Okay, it tells me that I think I did well trying to replicate what the author did. Before I conclude, I just want to mention here is this paper is not really the best paper, I guess, when it comes to novelties, the novelties, new piece of information with regard to pyrolysis or biomass, because they just simply use a normal setup, normal blocks. There are no introduction of new kinetics. There are no introduction of maybe MATLAB or maybe data validation or whatever, But the good thing about this paper is so simple to a point where you can get it done in just simply a few hours. So this paper would be a good training because you can compare apple to apples. If you use I would say more recent papers or the papers that are published in a higher rank journal, you will see they are more complex, they have more details, they use a kinetics, maybe that focus on char formation, kinetics that really takes into account other things, which I don't really know. I'm not really an expert on this, but my point here is this paper, although it is a quite simple paper, there are nothing novel about it, but I think it is a good paper for you to refer to and then to compare your result, because it is so simple. There are no new piece of information that you need to provide, and you don't need a lot of effort when it comes to collecting data, and making sure that your simulation is correct. Okay, guys, I think that would be all from me. I decided to divide this video into two, I guess, because it's too long. So yeah, I will upload one by one. So it's going to be two-part videos on biomass gasification and pyrolysis. Yeah, that's pretty much all from me. As I said before, I said one more time, I am not really an expert when it comes to biomass. So biomass conversion, blah blah. I'm also not really an expert when it comes to pyrolysis, in terms of like their definition, the exact temperature, their kinetics, stuff like that. Which one's more favorite. But when it comes to simulate pyrolysis or gasification, they are more or less the same. So the fact that I'm able to simulate and then have a same result with the paper kind of like suggests that what I do is technically correct, despite me not being really an expert when it comes to biomass conversion processes, thermochemical, biochemical, or even chemical processes. All right, that will be all for me. If you like the video, give it a thumbs up. Consider subscribing to my channel. I'm trying to make money here, so I try to watch a lot, and then maybe you can invite your friend to subscribe to my channel. Or if I can get like 1,000 subscribers, that would be really nice. And then if you can, another issue is basically I'm trying to retain the viewers, because somehow when it comes to highly specific piece of information or knowledge or skills, people tend to not really interested with this thing. So yeah, I will see you next in the next video. Have a nice day and happy new year, I guess. I know it's quite early, but happy new year in advance. All right, bye bye.